Good morning, everybody. Hope you are all healthy and safe at home. So, let us continue our session. Module 1, Chapter 1, Section 1.1. So, in the previous session, we had winded up with defining what a norm space was. So, it is basically a linear space along with the norm function. And I had asked you to go through the examples which were given in page number 8. Hope you guys have done that. So in that example, we can see that the space LP, where P is greater than 1, it cannot be easily shown that it is a linear or not. Now to show that that space is linear, we have to first verify that the norm P that we have defined, that is norm P of x is equal to summation mod xi whole raised to P whole raised to 1 by P. We have to show that that norm satisfies the triangular inequality. Both the other properties of norm are easily solved or easily seen, but this property cannot be shown as much easily as the case when P is equal to 1. So once we show that the norm that we have defined satisfies the triangular inequality, it is easy to show that it is a linear space. Now to show that, to prove that this norm satisfies the triangular inequality, we have to first prove two other inequalities. One is the Holder's inequality and the other the Minkowski's inequality. So let us try to prove the Holder's inequality. Now what does Holder's inequality states? The Holder's inequality states that for every sequence of scalars, sequence AI and sequence BI, and for 1 less than P less than infinity, we have modulus summation AKBK is less than or equal to summation mod AKBK, which is further less than or equal to summation mod AK whole raised to P whole raised to 1 by P into summation mod BQ whole raised to BK whole raised to Q whole raised to 1 by Q, where 1 by P plus 1 by Q equal to 1. So let us try to prove this theorem. So what is given to us? We are given two sequences, sequence AI and sequence BI. Now first note that we will prove this theorem for the finite case, that is when I varies from 1 to n, and when we apply limit n tends to infinity, we obtain the infinite case. We are considering two sequences, so they can be finite or infinite, so we have to prove for infinite case. So to prove this, we are going to prove only the finite case, because once we have proved the finite case, by tending n tends to infinity, we can easily see the infinite case. Now, before moving to the proof, we are given in the theorem or in the inequality that 1 by P plus 1 by Q is 1. So using this equation, we can form two other equations which we will further use in our proof. So from this we can say that P plus Q equal to PQ by just taking the LCM and rearranging it, we get PQ minus Q is equal to 1. So this implies we can take Q common. P minus, sorry, not 1, it is P. P minus 1 into Q equal to P. Similarly, we can also get another equation, that is 1 by P minus 1 will be equal to Q minus 1. So using 1 by P plus 1 by Q equal to 1, we get P minus 1 into Q equal to P, and 1 by P minus 1 equal to Q minus 1. So now let's move on to the proof. First we will suppose Ci is equal to mod AI by summation mod AI whole raised to P whole raised to 1 by P, and Di is equal to mod Bi by summation mod Bi whole raised to Q whole raised to 1 by Q. Then what will be summation ci raised to p. This will be summation mod ai by summation mod ai whole raised to p whole raised to 1 by p whole raised to p. So that is summation mod ai, taking the power inside, and p and 1 by p gets cancelled, so this will be summation mod ai raised to p. So finally we get to be 1. Similarly, we can show that summation di raised to q is 1. So by our definition of ci and di, we can show that summation ci raised to p equal to 1 and summation di raised to q equal to 1. So first we will check that. First we are going to verify that summation or ci di that we have defined, ci di will be less than or equal to 1 by p ci raised to p plus 1 by q di raised to q. This is what we are going to show, and from this, taking summation on both the sides, we will get the required inequality. So before that, what we are going to prove is that we are going to consider two functions, that is y is equal to x minus c. You can see it in your textbook that we are considering two functions, y equal to x raised to p minus 1, and then using this function we can obtain another function, that is x is equal to y raised to 1 by p minus 1. Now what we are going to do is we are going to integrate the function y equal to x raised to p minus 1 from 0 to ci and obtain the area S1, and we are going to integrate the function x is equal to y raised to 1 by p minus 1 from 0 to di and obtain the area S2. So let us see how we can do it. Consider, we are considering the function y equal to x raised to p minus 1 and integrating this function with respect to x. What do we get? We get integral y dx will be equal to integral of x raised to p minus 1 into dx, and from where to where? From 0 to ci. What will be this value? This will be x raised to p whole by p from 0 to ci. What is the value? Value is ci raised to p by p, and we denote this by s1. So we have s1 is equal to ci raised to p by p. Similarly, if we consider the function x is equal to y raised to 1 by p minus 1 and integrating this with respect to y, varying with the variation 0 to di, we again get the value 1 by p, 0 to di, we get the value by 2, that is 1 by q into di raised to q. You can just verify it, and a similar integration is easy. And for this, here we substitute the value of 1 by p minus 1 to be equal to, what did we get? We got it to be q minus 1, that is y raised to q minus 1, and we can integrate it in a similar manner just as we did before. 1 by p minus 1 is q minus 1, so we can obtain the value to be 1 by q into di raised to q, and we denote it by s2. Now by the properties of integration, we can see that the product ci di will be less than or equal to s1 plus s2, that is 1 by p into ci raised to p plus 1 by q into di raised to q. So we obtained that Ci into Di is less than or equal to Di is less than or equal to 1 by P Ci raised to P plus 1 by Q Di raised to Q. Now taking summation on both the sides, what do we get? We get summation Ci Di is less than equal to 1 by P is common, summation Ci raised to P plus 1 by Q into summation Di raised to Q. Now we have seen that summation Ci raised to P is 1 and summation Di raised to Q is also 1. So what will this value be? This will be 1 by P plus 1 by Q. And in the theorem it is given that this is equal to 1. So what have we got finally? We have got that summation Ci into Di is less than or equal to 1. Now let us substitute the value of Ci and Di. What will it be? It will be summation mod Ai by summation mod Ai raised to P whole raised to 1 by P into mod Bi by summation mod Bi whole raised to Q whole raised to 1 by Q will be less than 1. Now taking the denominator to the other side, what do we get? We get summation mod Ai Bi will be less than or equal to summation mod Ai whole raised to P whole raised to 1 by P into summation mod Bi whole raised to Q whole raised to 1 by Q. So this is the required inequality. So the proof was much easy to prove. We just have to substitute the value or substitute Ci is equal to mod Ai by summation mod Ai whole raised to P whole raised to 1 by P, and Di is equal to summation mod Bi whole divided by summation mod Bi whole raised to Q whole raised to 1 by Q, and solve it. The proof is much simple. Now we can see that when we consider, you can note that when P equal to Q equal to 2, then the above inequality is called the Cauchy-Schwarz inequality. So if you are asked to prove Cauchy-Schwarz inequality, what we must do? We must prove the Holder's inequality for the case P is equal to Q equal to 2. Also, by defining summation BQ whole raised to Q whole raised to 1 by Q to be the supremum BK, we can for Q equal to infinity, we can also solve it trivially. Now next I would like you guys to do theorem 1.2.4. It is similar to the inequality, Holder's inequality. The proof is similar except that instead of summation we have the integration part. So I want you guys to try to prove the same. Now let us move on to, as I had mentioned before, we have to prove two inequalities. One was the Holder's inequality and the other the Minkowski's inequality. Now what does the Minkowski's inequality state? Minkowski's inequality states that for every sequence of scalars A equal to sequence Ai and B equal to sequence Bi, and for 1 less than or equal to P less than or equal to infinity, we have norm P A plus B is less than equal to norm P A plus norm P B. So the one thing that we must note in this inequality is that, or in this inequality is that we are using 1 less than or equal to P less than or equal to infinity. In Holder's inequality we had just mentioned about the cases. We did not consider the case 1 equal to P and P equal to infinity, but in Minkowski's inequality we consider both these cases also, and also we will use Holder's inequality to the proof of Minkowski's inequality. So let us begin with the proof. So first let us consider the case P is equal to 1. Now when P is equal to 1, what do we have to prove? We have to prove that norm 1 of A plus B should be less than equal to norm 1 of A plus norm 1 of B. Now what is norm 1 of A plus B? This is nothing other than summation mod AI plus BI whole raised to 1 by 1, which is summation mod AI plus BI. And we know this is always less than equal to summation mod AI plus summation mod BI. Now what is summation mod AI? We can rewrite this as norm 1 of A, and this can be written as norm 1 of B. So we have obtained that norm 1 A plus B is less than equal to norm 1A plus norm 1B. Now next we consider the case P equal to infinity. That is norm infinity of P, norm infinity of A plus B. What will be it? By definition it is supremum of mod AI plus BI. Now we know by supremum property this is less than equal to supremum of mod AI plus supremum of mod BI. Now what are these? These is nothing other than norm infinity of A plus norm infinity of B. So in case when P is equal to infinity, we have obtained that norm infinity A plus B is less than or equal to norm infinity A plus norm infinity B. So now let us consider case 1 less than P less than infinity. So this is basically the same inequality that was mentioned in the Holder's inequality. So I had told before that to prove Minkowski's inequality, we are taking the help of Holder's inequality. So now let us consider norm P A plus B whole raised to P. This can be written as summation mod AI plus BI whole raised to P whole raised to 1 by P, and we are taking norm P whole raised to P, so this is whole raised to P. What is this? This value would be norm of AI summation AI plus BI whole raised to P. P and P gets cancelled. Now this is this can also be written as, we can rewrite it as summation mod AI plus BI whole raised to P minus 1 into AI plus BI. Now using the triangular inequality, what do we get? We get this is summation mod AI plus, we apply the triangular inequality to this part and we get this as mod AI plus mod BI. Now opening the brackets, what do we get? This is equal to summation mod AI plus BI whole raised to P minus 1 into mod AI plus summation mod AI plus BI whole raised to P minus 1 into mod BI. Now next what we are going to do is we are going to apply Holder's inequality to this part and to this summation separately. So what do we get? We get norm P A plus B whole raised to P will be less than or equal to summation mod AI whole raised to P whole raised to 1 by P into summation mod AI plus BI whole raised to P minus 1 was the term, whole raised to Q whole raised to 1 by Q plus summation mod BI whole raised to p whole raised to 1 by p into summation mod ai plus bi whole raised to p minus 1 whole raised to q whole raised to 1 by q. Now, what is the value of p minus 1 into q? We have seen that p minus 1 into q is nothing other than p itself. So, this can be written as summation mod ai whole raised to p whole raised to 1 by p into summation mod ai plus bi whole raised to p whole raised to 1 by q plus summation mod bi whole raised to p whole raised to 1 by p into summation mod ai plus bi whole raised to p whole raised to 1 by q. So in this you can see that the term summation mod ai plus bi whole raised to p whole raised to 1 by q is common. Now we can see that norm p a plus b whole raised to p will be less than or equal to summation mod ai plus bi whole raised to p whole raised to 1 by q into summation mod ai whole raised to p whole raised to 1 by p plus summation mod bi whole raised to p whole raised to 1 by p. Now what is summation mod ai whole raised to p whole raised to 1 by p? That is nothing other than the norm. So we can replace this by norm p of a and norm p of b. Now taking this term to the left hand side, what do we get? We know that this value is summation mod ai plus bi whole raised to p whole divided by summation mod ai plus bi whole raised to p whole raised to 1 by q b less than equal to norm p of a plus norm p of b. Now simplifying this, these both the terms are same, so this will become summation mod ai plus bi whole raised to p 1 minus 1 by q will be less than equal to norm p of a plus norm p of b. Now what is 1 minus 1 by q? That is nothing other than p. 1 by p mod ai plus bi whole raised to p whole raised to 1 by p is less than equal to norm p of a plus norm p of b. This implies this is none other than norm p of a plus b. So we have got norm p of a plus b is less than equal to norm p of a plus norm p of b. So this is our proof of the Minkowski's inequality. That is, if you are considering two sequences a equal to sequence ai and b equal to sequence bi, and for 1 less than equal to p less than equal to infinity, we have norm p of a plus b is less than equal to norm p of a plus norm p of b. So with the help of these two inequalities, we can show that the norm p satisfies the triangular inequality, and further we can show that the space LP forms a linear space. Now again we have theorem 1.2.6, which is also similar to Minkowski's inequality, except that instead of summation we have the integration part. So I want you guys to verify theorem 1.2.4 and 1.2.6 and see whether you can see whether the concept of the proof of these two inequalities are clear to you. So that's it for today. Thank you. Stay home and stay safe.